Hello everyone, so we want to show the beta function is a valid probability density function. I have written down the form of the density function, which is given by 1 over beta alpha comma beta. Those are the parameters of the beta function, times x to alpha minus 1, 1 minus x to beta minus 1. And the alpha and beta, which are commonly known as shape parameters of the beta distribution, are both positive, and domain of random variable x is between 0 and 1. So in order to show that this is a valid density function, we need to do two things. One, we need to show that the function is positive. Okay, and this is true. This is indeed true for beta function, because beta density function, I should say, because beta of alpha and beta is positive, and in the interval from 0 to 1, x to alpha minus 1 and 1 minus x to beta minus 1 will also be positive. Remember, alpha and beta were positive themselves as well. Okay, so we established the first fact. The second thing, which takes more work to do, is to show that the area under the curve over the domain is 1. I'm just going to write the area is equal to 1 over the domain from 0 to 1. Okay, now with that, in order to do that, therefore, we need to show that the integral of f of x alpha beta, namely what's in the beginning statement that I have here, that integral is equal to 1. Okay, from 0 to 1. So that's what we need to do. Okay, now if we can do that, then we're good. Now, just a comment here, this coefficient on the density function 1 over capital B, which stands for beta function, we commonly call that the normalizing factor. So pretty much what it means is the following: everything else that's to the right of that, namely this in here, once we integrate that, that should equal to beta function parameters alpha beta. Okay, so if we can show that the integral of x to alpha minus 1, 1 minus x beta minus 1 is equal to the beta function, then multiply by the reciprocal of beta function, and we get what we desire here. So let's begin. What are we going to do first? I'm going to start by letting p be alpha minus 1 and q be beta minus 1. Okay, so that if I write p factorial and q factorial, that's going to be the integral from 0 to infinity of x to p e to negative x dx. Now again, these are the gamma functions. Okay, these are the gamma functions. They're not the integral we started with. And the integral from 0 to infinity y to q e to negative y dy. And in here, both x and y, of course, are positive. Okay, so I have written the gamma function for p factorial and q factorial. Now, if you put them together, therefore, product of p factorial times q factorial is going to be the double integral from 0 to infinity of x to p y to q e to negative parentheses x plus y, and then dx dy. Okay, now at this point we're going to make our transformation. So the transformation that I'm using is, let the ordered pair xy be transformed into a UV coordinate system. So x, which is a function of UV, therefore, is going to be the product of UV, and y, which is another function of UV, is going to be 1 minus u times v. Okay, and once we add these two, we're going to get x plus y is equal to v. Okay, now let's see what we're gonna do next. So if I let x be uv again, we just showed v is x plus y, right? So u times x plus y, which is v. From this, we can solve for u in terms of x and y. Because remember, we're going to change all the x, y's to u and v. So that's why we need it. And we also need the limits of integration for u and v. Therefore, let's take a look at this work now. The fact that xy, I may not put parentheses, xy are positive, therefore u has to be positive, right? In here, if x and y are positive, so u has to be positive. Now, that establishes a lower bound for u. Now, in order to take a look at this as x and y, because remember, x, y greater than 0 means they lie between 0 and infinity. We're working on this part of it now. What happens around infinity? Okay, so to do that part, I'm going to say, suppose if x is fixed and we're going to allow y to go to infinity, then u approaches 0. And it has to approach 0 from the right, correct? Because u is positive, so it can't be negative. So u is going to approach 0 from the right. And then another time, I'm going to let y be fixed and allow x to go to infinity. When that happens, u approaches 1. Okay, and you can see that in this expression again. Fix y. Okay, so you have x over x plus, if you fix it, you can think of it as a constant, right? So the limit as x goes to infinity is just going to be the ratio of x to x. The constant don't matter, no matter how large or how small they are. Okay, therefore u approaches 1. Now, the question we don't know is it approaching 1 from right or left, right? We're hoping that it's going to approach from the left. So let's finish this work. This time let both x goes to infinity and y goes to infinity. And remember, x is less than x plus y, right? Because they're both positive. So that tells me that the ratio, if you divide both sides by x plus y, because x plus y is positive, you don't need to change the direction of inequality. That ratio is less than 1. So that tells me that u is less than 1. Therefore, it approaches from left. Okay, and putting all of this information together, therefore, we established the limits of integration that's coming. Limits on u is going to be from 0 to 1. That means the domain of u. Domain of v, well, let's see, domain of v, let's establish this one. For domain of v, well, y is 1 minus u times v, correct? And therefore, v is y over 1 minus u. And we did mention that u is between 0 and 1. Now I'm going to write it like this. I know it's a funny way of writing. Usually we write it the other way. I'm going to subtract 1 from, or I'm sorry, multiply everything by negative 1. And when I multiply by negative, now I have to change the direction, don't I? It's going to be less than 0 greater than negative 1. And then add 1. Add 1 to all parts. I get 0, 1 minus u less than 1. And that's what I wanted. See, the reason I had this backward inequality is because I was looking for 1 minus u. I could have done it to where I flipped the inequality at the end, but this worked out just fine. Okay, so 1 minus u established. This is between 0, 1, right? This is between 0 and 1, so it's positive. Y is positive, therefore V has to be positive. True? And there we have it. So domain of V, therefore, for the domain of V, we can say because Y is between 0 and infinity, and the denominator is between 0 and 1. The numerator is between 0 and infinity. Therefore, V has to be between 0 and infinity. Cool. So we now have the limits of integration for V as well as for U, those two new variables. Now we should be able to actually do this. Now the formula that we're going to use here is not really a formula, but from your third semester calculus, you can recall that the double integral over the region xy of fxy dx dy can be written as the double integral over the region under the new transformed variable uv with the joint distribution f of uv times absolute value of the Jacobian times du dv. And the reason we have absolute value on Jacobian is because we can name our function uv. For example, u is blah blah blah, v is blah blah blah. Well, I could have called this v, this u, right? I mean, functions don't care what we call them. But as we change the name here, we actually change the order, and I'll show you in a moment, the order in which these functions appear in the Jacobian. And because Jacobian is, let me write it, Jacobian is the determinant of a 2 by 2. So when you change the rows, it actually affects the value of the Jacobian. So that's why we need absolute value. So Jacobian is defined as the partial derivative of xy with respect to new variables uv. And the notation here, this notation is called d. Okay. And that is going to give me the determinant of dx. It's not absolute value notation, folks. It's just the determinant notation, because this quantity could be negative. So it's dx du and then dx dv, the second variable. So that's going to be dy du and dy dv. All right. And if we take the partial of x with respect to u, remember what x was here, right here. If we take the partial with respect to u, we get v. Partial with respect to v, we get u. Okay, so that's how I'm getting v here, u here. Now if we look at function y, remember what y was. I'm sorry, v. V is this one right here. Okay, if you take the partial, actually, let me go back to y, right in here. If you take the partial with respect to u, you simply get a negative v. Partial with respect to v, you get 1 minus u. Okay, in this. So let me copy what I just said here. 1 minus u. And of course, for a 2 by 2 matrix, the determinant is going to be the product of the diagonals minus the product of the off-diagonal elements. And that's going to give me v. Good. So we have all the components of this double integral. Let's put it together. Therefore, p factorial q factorial is going to be the double integral 0 infinity 0 to infinity of, I'm just recalling what those are in terms of x and y. Okay, and so this is going to equal to 0 to infinity, 0 to 1. X was uv to p power, and y was 1 minus u times v, y is to q power. Okay, to q power times e to negative v, and of course the Jacobian absolute value of v du dv. All right, but then v is positive, right? There you go. V is positive, so we don't need absolute value on v. Okay, next I'm going to collect the u terms and v terms together. All right, so that's going to make it integral from 0 to infinity, 0 to 1 of u to the power of p, 1 minus u to the power q times v to the power of p plus q minus 1 times e to negative v, and then du dv. And this is going to equal to, now I'm going to separate these two integrals. All the factors or terms that have v in them, I'm going to get them together. That's going to be these two. So it's going to be v to the power of p plus q minus 1 times e to negative v dv, and then multiplied by the ones with q, 0 to 1. Oh, I'm sorry, the one with u is going to be u to p, this one, and 1 minus u to q power, and then du. Okay, now going back to the v, by the way, here I have v to a power of p, v to a power of q, right? And then I have v here. All right, so actually that's going to be positive 1, right? So when I combine them, that should be positive 1. Okay, I think that looks good. Let me real quick check. Yep. Yeah, I've got everything down correctly. I'm just checking on the exponents. All right, perfect. So the first integral that we're looking at, that's simply p plus q plus 1 factorial. Okay, that is the form of gamma function. Now the integral from 0 to 1, u to p, 1 minus q to that. Call this, yeah, there you go. That's what that integral is. U to p, 1 minus u to q du. Remember, all of this should equal to, the left side is p factorial, q factorial, right? So when we solve the integral, right, the integral, we're going to solve for that integral. U to p, 1 minus u to q du. That's just going to be p factorial, q factorial over p plus q plus 1 factorial, right? Now recall that I let p be alpha minus 1 and q replace beta minus 1 in the original expression when we started this video. Therefore, the integral from 0 to 1 of u to replace p with alpha minus 1, 1 minus u, q, let it be beta minus 1, and then du is going to be p, which is alpha minus 1 factorial times beta minus 1 factorial divided by alpha plus beta minus 1 factorial. And this is the very definition of beta, of alpha beta. Okay, therefore we showed the integral. The integral is beta alpha comma beta. Remember up here in the very beginning, I said if we can show that this integral is beta of alpha beta, then we pretty much have this down. Now, let me put it together then. Thus, 1 over beta of alpha comma beta. I'm working with the full density function now of 0 to infinity, 0 to 1, x to alpha minus 1, 1 minus x to beta minus 1 dx. Therefore, is going to be simply beta of alpha beta over beta of alpha and beta, right? These look the same, right? Remember, these variables are just dummy variables. The name doesn't matter. X, U, W, they're just variables. And that is equal to 1. And that's what we wanted to show. So, looks like beta is a valid probability distribution. And that will conclude this video. Thank you for watching.